Hi everybody, welcome to our lecture on light. We're going to talk about light and its properties, and then later on we'll be eventually talking about the idea of something called optics. Now, the ancient Greeks viewed light as particles, and they called these particles corpuscles. And one of the reasons they believed people could see was that these particles somehow entered our eye and stimulated the whole process of vision. Now, later on in physics, the idea of light becoming a particle or being made up of particles was picked up by some pretty big guys in physics, Isaac Newton, Albert Einstein, and Max Planck. And these particles were given a particular name. They're called photons. Photons were interesting because they were particles that had no mass, thus having the ability to travel at the speed of light. So essentially, they were simply packets of energy. And that's how they were viewed at, particularly by Einstein and Planck's day. However, there are other physicists that believe that light was not a particle, but was actually acted like a wave. Christian Huygens was a big proponent of this. A guy named Thomas Young did this famous thing called the double slit experiment that seemed to show that light exhibited all the properties that a wave does. So, who's right? Well, maybe they both are. The idea is that light has sort of a dual nature. If you set out to prove that light acts like a particle, it will. If in turn you set out to prove that light acts like a wave, it will do that too. Here though in this lecture, we're going to focus on the wave nature of light. And one of the reasons we're going to focus on it as a wave is because it exhibits these very specific properties that we have seen with waves. First of all, light will reflect. In other words, if it hits a boundary, it will bounce off of it. Light will also refract. In other words, as light travels from one medium to another, it will bend due to that change in medium. Light can also diffract. In other words, it can bend around corners. If there's a darkened hallway but a door is open where there's a light on in the other room, there isn't sort of a light-shaped door on the far wall. There's sort of just light that spreads out because it can bend around that corner. And then light can also be made to interfere. In other words, two light beams can come together, and this is what Young proved with his double slit experiment, and you could get regions of constructive interference, brighter light, but you also could get regions of destructive interference, in other words, darkness, which is kind of neat in itself. One of the things to help us, though, in understanding the idea of light is we're going to use something called a ray approximation. Now, what that means is that instead of trying to show a light beam as some sort of wave coming in and striking something or going in any particular direction, we're going to represent it as a light ray, in other words, sort of an arrow, a beam of light in this case. Now, one of the first processes, of course, that light undergoes is the idea of reflection. When light strikes a boundary that exists between two media, in other words, as light goes from air to glass or glass to water, there has to be a boundary between the air and the glass or the glass and the water. And when light strikes that boundary, some or all of it will be reflected off of that boundary. Now, that reflection can also be based on what the boundary actually looks like. For example, if you have a nice smooth boundary, you can get a very, very sort of perfect reflection off of it, much like a mirror or something like that. However, if the boundary is kind of broken up, it actually can sort of disperse the light. Now, what do I mean by that? Well, light isn't just, of course, a single beam of light. It's a lot of beams of light, if you really want to look at it. And they all sort of travel together. So if they all come into a boundary together, sort of parallel, and the boundary is nice and smooth, then they'll all reflect together as sort of a bright light. Okay, that's if the boundary is nice and smooth. However, if you have sort of a more rough or broken boundary, even though those light beams come in together, the broken nature of that boundary can cause them to reflect in very different directions, okay, dispersing or spreading out the light. An example of the rough surface would be if you're driving down the road on most days that are dry, the sunlight strikes the road, but you don't get a glare off the road because then that broken road disperses the light in all directions. But if it happens to rain, the water will smooth in those rough cracks, and then if the sun comes out, you get a huge glare off of that nice smooth surface, okay, depending on how that really goes. So, to begin with, we have something called the law of reflection. And it has to do with that light actually bouncing off of something. And it says that the angle of incidence equals the angle of reflection. Well, what does that really mean? If a light beam comes into a boundary, let's say between air and water, well, it's going to strike that boundary at a certain angle. But the way we measure angles when we talk about light is we first draw what's called a perpendicular or normal line to the boundary. And so the angle that we measure is this angle here that we're going to call theta 1. And theta 1 stands for the angle of incidence. Okay? To be incident upon is sort of to happen upon, anything like that. Now, of course, when it strikes the surface, all or part of it is going to bounce off of that surface, also forming an angle over here we're going to call theta 1 prime. And theta 1 prime stands for the angle of reflection. So, what does the law of reflection really say? That theta 1 equals theta 1 prime. To give you sort of a demonstration of that, what we've got here is a little laser beam. And we have air, and in this case we'll have water. And notice there's a normal line that's already sort of drawn here. I'm going to put this little protractor so it's sort of right on that normal line there. Now, if I fire that beam, let's say it forms an angle of 30 degrees here, what you can notice right here is the reflected beam, which is also at 30 degrees. Okay, we'll talk about this other beam here a little bit later on. If I move it to 60 degrees, the reflected angle is 60 degrees. So clearly the angle of incidence and the angle of reflection are the same thing. And it doesn't matter. Let's say if I change this to glass. That didn't change that. Let's say I change this to water. Okay? That still didn't change it. No matter what the different boundaries and materials are, that angle of incidence and angle of reflection don't change. Now, where you're not going to get any reflection is if there's no change in boundary. If there's no change in medium, there's no boundary, there is no reflection. So there has to be two different media in order for reflection to occur. So now we can use the law of reflection and some good old geometry, and we all love geometry, to understand how light can be made to bounce off, for example, several mirrors. So, for example, let's say we have two mirrors, and we set them at an angle of 120 degrees to each other. And then we fire a light beam at an angle enough to strike one mirror, bounce off of it, hit the next mirror, and bounce away. And let's say that the angle of incidence, or I'm sorry, the angle that we strike the mirror here is measured to be 35 degrees. And we want to know what the reflected angle is off that second mirror. Well, first if we sort of just draw a normal line, right where that first reflection occurs. Well, if that angle there is 35 degrees, then this angle must be 55 degrees. And that's just a little geometry, adds up to 90. Now, 55 degrees is an angle of incidence, theta 1. So the angle of reflection has to also be 55 degrees, which of course, by geometry, would still make that 35 degrees. Now, we have one big giant triangle here, and there's 180 degrees in a triangle. So if we have a 35 degree and 120 degree angle, the remaining one must be 25 degrees. If I now draw a normal line here, and that is 25 degrees, well, that means that this angle here has to be 65 degrees, forming a 90-degree angle. That's an angle of incidence for this mirror, and therefore the angle of reflection, the one we're looking for, must also be 65 degrees. Again, just a little geometry, right? The second property light can undergo is a process called refraction. Now, for light to refract, it has to be able to go from one medium to another. So it has to cross the boundary. The boundary must be transparent. And as any wave, as we know, when it changes medium, will bend due to that change in medium. But because it's also going to strike the boundary, part of the ray is reflected while another part is refracted. So if we look at this now, let's bring this back to 30 degrees. We have an angle of incidence of 30 degrees, and part of my light beam is being reflected off the water here. But you'll notice that the beam that enters the water is no longer at 30 degrees. In fact, it's been bent some towards that normal line. And that's an interesting thing in itself, that it bent towards the normal as it went from the air to the water. So by changing medium, it actually physically bent that light ray. And that's what refraction is. Now, why it bends has something to do with what's called the index of refraction, which we symbolize with a letter N. The index of refraction is a ratio. It's the speed of light in a vacuum over the speed of light in another material. And that has to affect a lot of things. Not only how fast does the light go, but how much does it actually bend. So, for example, let's take a look at light being shined, for example, through a piece of glass. The light comes in and strikes the boundary between the air and the glass at an angle θ1, the angle of incidence. And then, as we saw in that other example, the light beam is bent from that path to some other angle that we're going to call θ2 later on. But then as it emerges out of the glass back to the air, it's actually bent again. And I'm going to call this angle θ3 right now. Now, as you might guess though, θ1 and θ3 are actually the same angle. And that's because they begin and end at the air, even though as they pass through the glass. But what's happened is that it's no longer along its original pathway. In other words, it's kind of been shifted a little bit. Strangely enough, means if you look out the window at a slight angle, you don't see things exactly where they are. They're kind of shifted a little bit. So, these N values, where the index of refraction comes in. N is C over V. Okay. So if I know that glass has an index of refraction of 1.5, that means I could determine how fast the light actually travels in the glass. Because the velocity in the glass would be the speed of light in a vacuum, 3 times 10 to the 8th, divided by the N value of 1.5, which gives you 2 times 10 to the 8th. Now, that brings up something interesting about index of refraction of itself. The letter C represents the speed of light in a vacuum, the fastest velocity you can get. So that means all velocities must be less than 3 times 10 to the 8th for all other media, which means that no N value can be less than 1. All N values must be greater than or equal to 1. Okay, that's one interesting thing about the N value. The other thing is that it can have no units. Because it's a ratio of velocity to velocity, the units would cancel out. So N is one of those rare physics things that actually doesn't have a unit related to it. Now if we look at this example again, for example, the air going into something like water, or even let's try glass. Okay. We'll notice that the angle of incidence here is 30 degrees as it comes in. Okay. Actually, I'm going to change that slightly to about 40 degrees. Of course, it's reflected off that boundary at about 40 degrees, but then it also bends. That's something that looks somewhere around 25 degrees or so from that normal line. Okay, so how do we know how much that bend is actually going to be? Well, to understand that, we use something called Snell's law for refraction. And Snell's law gives what those angles will sort of look like. The equation looks like this. N1 sine θ1 equals N2 sine θ2. The 1 is where the light ray begins, the 2 is where the light ray ends. So, for example, air and glass at 40 degrees. The 40 degrees is θ1, my angle of incidence. My light ray is going to then bend to some new angle θ2 that I want to figure out. So, using Snell's law of refraction, N1 sine θ1 equals n2 sine theta 2. Well, we begin in the air, so that's what n1 is, at 40 degrees. We end in the glass, so n2 is 1.5 sine theta 2. So if I take 1 times the sine of 40 divided by 1.5, that gives me 0.43 equals the sine of my angle. So of course, to get my angle, I need to take the inverse sine, and I end up with 25.4 degrees. Well, isn't that interesting? Because that looks just like this picture here, right around 25 degrees. So hey, Snell's law must work. What about when I come back out? Okay, to this new angle, I'll call theta 3 for a moment. Well, now I'm starting in the glass and I'm coming to the air. So if I start in the glass, n1 becomes 1.5, my beginning point. And now, what's theta 1? Well, if theta 2 here is 25.5 or 25.4 degrees, then this angle here is also 25.4 degrees. One of those sort of alternate interior angle rules from, yes, geometry. So the angle of incidence is 25.4 degrees. Now I end in the air, so the end value over here is 1, sine my new angle, and lo and behold, that should give me 40 degrees, exactly as it should. So if we look at this example here, and we're going to be beginning somewhere around 25 degrees, and we're going to start in the glass. So now if we reverse the situation, as we said before, and in this case we're starting in the glass somewhere around 25 degrees and ending in the air, you'll notice we'll end pretty much right around 40 degrees if I were to be able to get it exactly right. Something more like that. So Snell's law works either direction. Now, the one time you definitely don't have refraction is if your angle of incidence is right down the normal line. In other words, you have an angle of incidence of 0. And that's because, one, mathematically, the sine of 0 is always going to give you 0 degrees. So if I look at this, if I do this right down the normal line, as you can see, there's absolutely no refraction at all. It goes straight on through. There's no bending of the light. No matter what material I begin or go to, as long as I go straight down the normal line, there is no refraction. So to recap some things. As light changes medium, both the velocity and the wavelength will change. Then the light ray will bend. But, as with all waves, once it is generated, the frequency remains constant. So that means if the velocity goes up, the wavelength is going to go up. But if the velocity goes down, the wavelength is going to go down. And so that leads to another version of Snell's law that deals with wavelengths. So we can figure out what new wavelengths are also going to be based on the index of refraction. N1 lambda 1 is equal to N2 lambda 2. Now, let's look at one large example that sort of puts everything together. A 600 nanometer light ray in air, so it begins in the air, strikes water, 1.33, at an angle of 35 degrees to the normal. So 35 must be the angle of incidence. And 600 nanometers would be my beginning wavelength. Okay, so this is sort of my wavelength 1, my beginning point, and this is my theta 1, my angle of incidence. So A, the very difficult question, determine the reflected angle. Alright, well, theta 1 equals theta 1 prime, and so that's just 35 degrees. That wasn't too tough, was it? Okay, now to figure out the refracted angle in the water, we're going to use Snell's law with the angles. We start in the air at 35 degrees. We end in the water. Again, we take 1 times the sine of 35, divide by 1.33, take the inverse sine of that, and we end up with an angle of around 25.5 degrees as the refracted angle. C. Determine the speed of light in the water. Well, speed of light has to do with index of refraction, and is C over V, or V would be C divided by the n value. C is that constant, 3 times 10 to the 8th. N of water is about 1.33, and you get 2.26 times 10 to the 8th. Notice a lot of our numbers are staying in that 10 to the 8th region. Okay? It's hard to slow down a light a lot. Part D. Find the wavelength of the light ray in the water. Now we're asking about wavelength changes, so that would be that other version of Snell's law, n1 lambda 1 equals n2 lambda 2. Now, because we are changing just the wavelength, this is one of those rare physics times you don't really necessarily have to convert your units. In other words, you could leave it like this. 1 times 600 equals 1.33 lambda 2, which gives you 451.1, but be careful, your units stay as nanometers, which is fine. Now you could have converted that to 600 times 10 to the minus 9, which would give you 451 times 10 to the minus 9, or actually 4.51 times 10 to the minus 7. Got to be careful of the units when playing around with the wavelength area here. That leaves us with part E, the frequency. Now be careful, because it says find the frequency of the light ray in the water. But you don't have to find it in the water. You can find it anywhere you know enough information. And for me, if I have information in air or a vacuum, that's the easier way to go. Because if I take the vacuum or air, I know the speed of light is 3 times 10 to the 8th. And I was given the wavelength in the air. Now this must be in proper units, 600 times 10 to the minus 9. And that gives me a frequency of 5 times 10 to the 14th hertz. Now, had I chosen to do the water, I have to be careful. I have to use the velocity in the water, 2.26 times 10 to the 8th, and I also have to use the wavelength in the water, 451.1 times 10 to the minus 9. So as long as I keep the right values together, I get the exact same number because frequency has to remain constant. It's also a good way to check. Okay, so that is our introduction to the idea of light and the process of reflection, where the angle of incidence of a light ray equals the angle of reflection, and the idea of refraction, that is, light changes medium, its velocity will change based on the index of refraction of that medium. Its wavelength can also change, and both of these will cause the light ray to bend as long as it enters at an angle other than along the normal line, other than 0 degrees. And of course, the fact that light acting like a wave will undergo these properties of things like reflection, refraction, diffraction, and interference. All right, we'll pick up there next time. See you then.